Alright guys, in this section we're going to just get into a little review of some of the basic families of functions, and then maybe see a couple we haven't seen quite as often or maybe never before, and just introduce them today and then kind of dig into them. But first off, we have linear functions, which of course are the first ones that generally get covered in algebra and pre-algebra, and of course we all know they're like a y equals mx plus b kind of thing, right? Some sort of slope and y-intercept. Cool thing about these, their domains are all real numbers, unless it's a vertical line, but then that wouldn't be a function anyways. But domain and range are going to be all real numbers, and nice and continuous and smooth and all that stuff. Then the second one you guys probably cover in Algebra 1 is the old quadratic function. Okay, of course we know its graph is a parabola. Okay, either opens up or down. Again, domains all real numbers. This is the general form here, ax squared plus bx plus c. Domain, again, all real numbers. The range depends on where the vertex is, right? These have a minimum or maximum, and all that good stuff. Next, probably haven't done much with these at this point, but a cubic function, if we were to graph y equals x cubed, okay, it kind of looks like this. Okay, and it can have more. It could have more terms. It could be more than just ax cubed. It could be ax cubed plus bx squared plus cx plus d. I just happen to graph the most basic one here. The thing you'll notice the difference here. The end behavior in these. One end goes up, one end goes down. Because again, it's a odd degree function. Okay, like a linear function. Domain is going to be all real numbers, and the range on all of these is going to be all real numbers as well. Alright, then a couple others here. We have radical functions, so the basic parent function of the square root of x does something like that. And remember the domain is not all real numbers, because since you have something under a square root, that thing cannot be negative. So that's going to restrict the domain. A lot of times they'll just start from a point, depending on if there's shifts and whatnot, and just extend in one direction. Okay, and it kind of flattens out, but it is actually growing to infinity. The end behavior on this one would be going to infinity. There's not a horizontal asymptote that kind of bounds the function. But the rational functions do have asymptotes, right? So the main parent function, the simple one, this looks like y equals 1 over x. That one again has some domain and range restrictions. Okay, we know x cannot be 0. You have a vertical asymptote at x equals 0 because of the denominator, right, not being able to equal 0. And this one in particular would have a horizontal asymptote at y equals 0 because the degree of the denominator is larger than the degree of the numerator. So that may shift around, or some of them have no horizontal asymptote, as we saw. But the graph of this one, if we remember, just kind of fills in these little quadrant 1 and 3, and things can be flipped around and shifted and stretched and all that stuff, all those transformations. But this is the basic shape, basic format, and kind of the basic properties. Alright, another one that we've probably come across, the old absolute value of x. So this one, again, since you're taking the absolute value, it's kind of avoiding the y values being negative, and it actually ends up looking like a V. Okay, it's similar to the parabola, that both ends go up. However, it's more pointed at the bottom. It's not a rounded vertex, it's a point. And again, these could be flipped or stretched and all that stuff. But generally, the domain is going to be all real numbers, and the range will depend on where the minimum or maximum are. Okay, the next couple, sine and cosine, the trig functions, we're going to talk about those in a little more detail in a minute. But they're basically these waves, right? Where if you remember sine, and again, I'm gonna review a little bit in here, but sine, the parent function for sine starts out at the origin, and then it kind of goes through this up, back to the middle, to the bottom, back to the middle, and kind of keeps going. And it's periodic; it repeats. Okay, it goes on forever. So the domain is going to be all real numbers. Okay, which is nice. There's no holes, no asymptotes, anything like that. But the range on these guys, they are what is called bounded above and below. Okay, Okay, depending on, you might remember we talked about amplitude. Okay, so there's these boundaries. They're not asymptotes, but they're kind of like horizontal lines that bound the function. It's like a boundary, and that again depends on the amplitude. For now, we're just going to kind of be interested in the basic, like recognizing the function. We're not going to be having to do graphs and all the formats until later in the semester. But for now, just kind of get used to seeing that and knowing the terminology and the domain and range and stuff. Cosine is a very similar function. The parent function cosine x, okay, if it doesn't have any transformations, is going to start up at its maximum, and then you're going to go to the middle, to the bottom, middle, back up, and on the ends it kind of repeats itself. It's also a periodic function. Okay, so again, its domain is all real numbers. Okay, but the range is not, right? Similarly to the sine function, it is again bounded above up here and below. Okay, and with the parent functions, the boundaries are y equals 1 and y equals -1. Now those can obviously be stretched if you have a multiplier on the outside. Remember, like if it was like 5 cosine x, it would then go up to 5 and -5. That would be the amplitude. But again, more on that later. Alright, and two others that are probably new that we will spend some time on later, but today we're just introducing the exponential function. Okay, like y equals some number to the x power. We're going to use a base of e as our example. E is an irrational number, like pi, that is approximately 2.71, and it just has a lot of applications in calculus and in like sciences and whatnot. So, but it could be, the base could be anything. We could y could equal 4 to the x, or y equals 10 to the x, or whatever. I've just happened to choose e as our base. The important part with exponentials is that the exponent is x. And what these do, and we're going to show a little more detail in a minute, but they kind of start out flat like this, and then the exponential growth always grows really quickly like that. Okay, and that's when the base is bigger than 1. Okay, and e, of course, like we said, is 2.71. But it actually does have a horizontal asymptote at y equals 0. You can see on the left end there, it's going to approach 0. Okay, then the other and final function, the logarithm function, okay, again, it can be any base. It could be log base 10 of x, could be log base 6 of x. If we're sticking with that e, okay, then we use, it's called the natural base, so we write it as natural log, and it's ln. And again, we have a whole chapter coming up on this soon. I just wanted to introduce so you see what the graph looks like at this point, so it's not totally brand new. But it's actually the inverse of the exponential function, so it kind of does one of these guys. Okay, and we're going to talk about just a second, a little more detail where these points come from, just to familiarize ourselves a little bit. And then again, there's a full chapter on all the details coming up down the road, so something to look forward to. Okay, so real quick, just to kind of remember where the sine and cosine graphs come from, and again, this is something we're going to do in full detail down the road as well, but they come from the unit circle, okay, where you have the center is 0, 0, and then if the radius of the circle is 1, right, the coordinates of this point, it would be 1, 0, okay, this one would be 0, 1, over here the x would be -1, y is 0, oops. And then down here we're at 0, -1. Okay, and let's just say if we wanted to graph, for example, the sine function, right, y equals the sine of x. Okay, what we do is we think about when you place a triangle in the unit circle, okay, something like that, right, there's some coordinates there, an x and a y value. Okay, and again, the idea is if we're focusing on sine right now, here's the right angle. Here's our actual angle theta that we're measuring. That's going to be our x values on the graph. Okay, so the sine of an angle, if you remember from SOHCAHTOA, sine is always opposite over hypotenuse. So in this triangle, the opposite side is that side, okay, which is the y coordinate of the point, right? That's the y distance. It's vertical. And the thing that makes the unit circle work, if sine is opposite over hypotenuse, right, the opposite we just said is the y coordinate, The hypotenuse, since this is a unit circle, the hypotenuse is always 1. Okay, we made the circle that size for a reason, and this is basically the reason. So the sine is always just going to be these y coordinates of the points on the unit circle. So when we plot them, okay, we put a 90 degree, a 180, a 270, and a 360 for our x values, because those are the angles as you move around the unit circle. Okay, and we'll be doing a lot more with radians, but I don't want to get too much going here until we get there. But basically the idea is, again, when you start, sine starts at 0. Okay, when you get up to the 90 degree, which is pi over 2 radians, the y value up there is 1. Okay, so I'll just put these in degrees for today. 90, 180, 270, and 360, right? Okay, when we get over to 180, the y coordinate is back down to 0. 270, the y coordinate is down to -1. Oops, that was in the wrong spot. Supposed to be over here. That was 270. And then when we get back to 360, the y coordinate's back to 0. And then it just starts to go around again. So you get this kind of wavy kind of thing, and it's going to keep going. Okay, and it would keep going this way as well and doing the same thing. And it just repeats itself over and over and over. So that makes the domain all real numbers. Oops, erased my L there. Sorry about that, a little sloppy. That's a lot better. I'm leaving that one. Anyway, so the domain on these are all real numbers, because again, it goes through all x values. And the circle just keeps going around and around. The x, again, is like the angle, and it could be anything. But the range, the new term that we need to be familiar with is, since this thing never goes above 1 or never goes below -1, it is bounded. So as an interval, it would be from -1 to 1. Okay. Or of course we could write it as a compound inequality there. Okay. And then cosine would be very similar. It would be the just using the x coordinates around the unit circle. Okay. And again, we're going to do a whole bunch of this later. This is just a quick recap on where the graph comes from and why it looks like it does. Okay, the other two functions that we hadn't really seen much, if at all, is that exponential function, y equals e to the x. So here's a graph. I just made this in decimals. I would encourage you guys, jump in decimals and look at these things as you're practicing. But basically, y equals e to the x. The idea is I just put a little table together. So x is the exponent. And you see in the table, when x is 0 right here, right, anything to the 0 power always equals 1. So that's kind of like our point that we're going to use as like our kind of key fixed point there. Okay, so e to the 0 power is 1. You see when x is 1, the value is just e to the first. That's the actual value of e. It's 2.7182818, and then it goes on forever irrationally. It's not a repeating pattern, even though it kind of looks like it. And then you see when x is 2, e to the second power is like the 7.39, and it just keeps growing and growing and growing, and this thing's just going to grow like an exponential growth. And then what's happening on the left, okay, like for example, at -1, right, e to the negative first power, a negative exponent means 1 over e to the first. Okay, so this is like 1 over the 2.71. And you can see from the table the value there's the 0.368 roughly. Okay, and as it even moves more and more, okay, as we keep going with that, e to the negative second, again, negative exponent means reciprocal. It's 1 over e squared, which is 1 over 2.71 squared. So the denominator's bigger, right? So it makes the whole fraction get smaller. And that trend, it just keeps continuing, and these points just keep getting closer and closer to 0, but they never quite reach 0. So that gives us a horizontal asymptote at y equals 0. Okay, the domain's all real numbers. This thing's going forever. But since it's just approaching 0 for a y value, The range then, if we take a look, it's never going to get to 0, but it does go up to infinity. So the range could be written as 0 to infinity. Okay, in other words, y must be greater than 0. Okay, not greater than or equal to, just greater than 0. All right, and the end behavior, just to state that, okay, as x goes to infinity, okay, look at the right side of the graph. Y is going up to infinity. And as x goes to negative infinity, okay, the left side of the graph, what are the y's approaching? 0, right over here. Okay, so that's some of the basics on that. Again, got a lot more detail coming, but just for now, recognize the shape. Like if you see that shape graph, we need to know that that is an exponential function. Was y equals e to the x. Same ordered pairs we saw in this example, just flipped. Okay, so the next one, the 7.39. All right, and finally the natural log function. Okay, or a logarithmic function. Y equals the ln of x. So this one, again, there's a lot of details. I'm going to just briefly kind of summarize some things, but basically a logarithm, it's going to be the inverse of what we just saw. Okay, so it means the x's and y's are switched. So basically the idea is natural logarithm is the same as having a base of e. So what this really means, it's really like e to the y equals x. So see how the other previous, this one is now x equals e to the y because they switched. Okay, and again, we're going to go a lot more deeper in this later. But just to see why the graph looks the way it does real quick, if we made a quick table, instead of choosing x values, right, because this one is solved for x, think about what happens if we choose some y values. Okay, so I know it seems weird, but just think about, let's start with when y is 0, right? When y is 0, we have e to the y power, e to the 0 power, right? Anything to the 0 power always equals 1. So this graph, like its kind of key feature, it's going to go through 1, 0, okay, unless it's getting shifted around and stuff. And then it kind of continues. If y were 1, e to the first is that 2.71, okay, which you see, where are we at, 2.71 for y, I'm sorry, 2.71 for x, and the y value is 1. That point is right about there. Okay, and then it's just all would be the x value now, and that's when y is 2, which is happening right about here. And this thing approaches the x-axis, so it actually has a vertical asymptote. Okay, so its domain is not all real numbers. Its domain is all x is greater than 0, okay, or 0 to infinity as interval notation. It's the range on this one that it's all real numbers. Okay, because again, it's the inverse of the previous, so the domain and range have been switched. Okay, this one does have a vertical asymptote at x equals 0. Okay, basically the y-axis. Okay, you can see right here. Right, so that's a vertical asymptote. End behavior on this one, as we're going to the right, as x goes to infinity, the y's are still going to infinity, it's just slowly. Okay, and there's really no left end behavior. As x goes to negative infinity, I don't know, NA, not applicable, right? It doesn't go to negative infinity, it's stopping right here. Okay, so again, a lot more on that coming, just a quick basic. You need to, at this point, be able to recognize the shape of the graph, and I just wanted to give you a little background on why it looks the way it does. Alrighty.